Let us discuss energy eigenkets. To be able to evaluate the effect of time evolution operator on a ket alpha, first we need to understand how this acts on the base kets which we are used to expand this state ket alpha. Here we are using base kets which are eigenkets of operator A such that commutator of AH equal to 0. This means the eigenkets of operator A are also eigenkets of operator H. That gets known as eigenkets of operator H, that is Hamiltonian, is known as energy eigenkets. Energy eigenkets, whose eigenvalues we used to denote as EA dash. Okay, that means if an operator, Hamiltonian operator operating on ket, base kets A dash, will get energy eigenvalue EA dash into base ket A dash. We can now expand the time evolution operator, in terms of outer product A dash, and let's take T naught equal to 0 for simplicity. Okay, that is, the time evolution operator is e raised to minus iht divided by h cross. I have already written the derivation because this will take to write this derivation will take more time. So to save time, I have already written, and I'll explain this. E raised to minus iht divided by h cross equal to sum of a double dash, outer product of a double dash, e raised to minus iht divided by h cross, outer product of a dash. Okay, this we can expand in this terms. I explained it earlier because sum of a dash, outer product of a dash equal to sum of a dash, outer product of a dash equal to 1, sum of a double dash, outer product of a double dash equal to 1. So we can write e raised to minus iht over h cross as in this way. Okay, that is equal to sum of this a double dash, sum of a double dash, this whole term means whenever a double dash comes, we can use a dash, then a double dash, then a triple dash, like that. So here we are expanding this, that is equal to sum of a dash. Let's keep this term here, and we can expand with sum over a double dash. That means first we have to apply a dash for a double dash, that is outer product of a dash e raised to minus iht over h cross, outer product of a dash, plus we will give a double dash for this value, so that is a double dash, outer product of a double dash e raised to minus iht over h cross into a outer product of a dash, plus next we will give a triple dash for this term, and we will expand and so on. Okay, so then that is equal to sum of a dash, outer product of a dash, e raised to minus iht over h cross, outer product of a dash, because when we are expanding this term onwards, we will get, here it's a double dash, here it's a dash. So if you are operating e raised to minus iht over h cross, if you are operating with this operator on a dash, we will get the same eigenket a dash, okay, and some eigenvalue. That eigenvalue, let me let me write e raised to minus I e a dash t divided by h cross. Okay, that eigenvalue into that base ket a dash. So if we are taking this eigenvalue, we can take outside, and then we will get inner product of a double dash a dash. That means inner product of a double dash a dash equal to 0 0, because a dash and a double dash are orthonormal set of orthonormal base kets, orthonormal kets. Okay, so that will give 0. So we need to consider only the first term, that is sum of a dash outer product of a dash e raised to ht divided by h cross outer product of a dash. So we can expand this term as we have expanded in equation 3, that is sum of a dash outer product of a dash. This term we can expand 1 minus iht over h cross plus minus I square divided by 2 h square t square over h cross plus etc. into outer product of a dash. Okay, this we can expand again, because we can multiply with these terms. Then we will get sum of a dash outer product of a dash into outer product we can multiply this with this one and then with this one. Okay, and the second term, if you are multiplying with outer product of a dash into outer product of a dash into iht divided by h cross into outer product of a dash, that means minus it divided by h cross we can take outside because it's constant values, and then outer product of a dash into h is operating on outer product of a dash. Okay, and the next term I have written here, h square is acting on outer product of a dash. In this way we can write the above step. Okay, that is equal to sum of a dash outer product of a dash. This is inner product of a dash equal to 1. So we will get outer product of a dash here, remaining outer product of a dash, that minus here also h is acting on a dash will give as in this equation h on a dash will get an eigenvalue, energy eigenvalue e a dash. So we can understand how this step got. So that is I e a dash t over h cross into outer product of a dash, and similarly next step 2 minus I square divided by 2h cross e a dash square t square. Okay, and into outer product of a dash plus etc. Okay, and then next step it will come like this, that is equal to sum of a dash outer product of a dash. Okay, let's take this outer product a dash outside, and then we can write this we are taking a common outside the bracket, and we can write outer product of a dash 1 minus I e a dash t divided by h cross plus minus I square divided by 2h cross e a dash square t square plus etc. So what is this term? This term is e raised to exponential minus I e a dash t divided by h cross. So this is an eigenvalue. It's a complex number, so we can write wherever we want, that is maybe in between this outer product or right after this outer product, doesn't matter in which way we are writing. So that is equal to sum of a dash e raised to minus e a dash t divided by h cross into bra a dash. Let's give a number to this equation. This equation 4. 3 equations we have already mentioned. This is equation 4. The importance of this equation is this equation enables us, this Actually this is e raised to minus iht over h cross. This is the form of an operator. This equation enables us to solve any initial value problem once expansion is happened. If this is alpha state and this we can expand in terms of base kets, and if once expansion is happened, then using this operator we can solve this kind of problems. For example, we can expand a state ket alpha that is equal to alpha t naught equal to 0. Okay, usually here in this dynamics, in this quantum dynamics, we used to represent a state ket like this. So this we can expand like sum of a dash, outer product of a dash alpha, we have learned earlier in this form, that is equal to this. This is the expansion coefficient, this is c a dash, so we can write this as sum of a dash c a dash a dash. Okay, we then have a state ket at a time t, that is t naught equal to 0 at a time t, equal to, how we can transform this state into this state. Just we need to operate, use an operator e raised to minus iht over h cross on this state ket. Okay, that is e raised to minus iht over h cross on state ket alpha t naught equal to 0. Okay, for simplicity we can represent e raised to minus iht over h cross alpha. Okay, this is an operator. This operator we can represent in the form of equation 4, that is this operator is sum of a dash e raised to minus I e a dash t over h cross a dash. Okay, and this alpha. Look at this. This term a dash alpha is c a dash. Okay, so we can write sum of a dash c a dash into e raised to minus I e a dash over e a dash t over h cross, and its base ket a dash. Okay, actually this c a dash is c a dash at t naught equal to 0, and this c a dash transforms into sum of c a dash of t into a base ket a dash. So what happens here? Here it was at t naught equal to 0, state ket alpha at t naught equal to 0 is equal to sum of a dash c a dash into base ket a dash. This c a dash has changed into c a dash of t, or c a dash has changed into c a dash of t. This is c a dash of t naught equal to 0. This has changed into c a dash of t, that is equal to c a dash e raised to minus I e a dash t over h cross. Okay, this change has happened at time t, and there is no change for this base kets. Expansion coefficient c a dash has changed into c a dash of t, that is c a dash e raised to minus I e a dash t over h cross. Okay, this expansion coefficient has changed, but its mode, that is c a dash e raised to minus e a dash t over h cross, that's equal to mode of c a dash. Its mode doesn't change, but this expansion coefficient has changed. Okay, let us take a special case, that is this alpha t not equal to 0, that is equal to base ket a dash itself. Base ket a dash itself means this alpha we can expand as c a dash a dash. Okay, this c a dash we are taking here 1, and this base ket a dash. Okay, and after time t, this state ket will become alpha t not equal to 0 t. So this will happen because an operator is operating on this state ket. That operator is, we know, it's e raised to minus iht over h cross alpha t not equal to 0. So alpha t not equal to 0, we know this is base ket a dash. So we can write e raised to minus iht over h cross a dash, and this is equal to e raised to eigenvalue. This is operating on this one. We have earlier proved that e raised to minus e a dash t over h cross a dash. This is actually eigenvalue. This is eigenket. Okay, this is eigenvalue and this is eigenket. Let us do an operation with h on this state ket at time t. Okay, that is alpha t not equal to 0 t. We will get e raised to minus I e a dash t over h cross into h is operating on a dash. Okay, if h operating on a dash, we will get e raised to minus I e a dash. H operating on this one, we will get this one. So h operating on a dash, we will get e raised to minus I e a dash t over h cross, and e a dash eigenvalue into base ket a dash. This we can write as e a dash e raised to minus I e a dash t over h cross a dash. Okay, this is equal to e a dash into, what is this one? This we have reached in this equation as a state alpha at time t. So that is equal to alpha t not equal to 0 t. Okay, that means if we are operating h on this one, we will get the same eigenvalue e a dash with this state ket. So at initial time, h is operating on base ket a dash, we will get an eigenvalue e a dash with ket a dash. That means, and here at time t, h is operating on the state ket, and we will get the same eigenvalue e a dash. That means if at initial time alpha is the simultaneous eigenket of a and h. Actually, in this beginning of this topic, we have taken alpha is the simultaneous eigenket of a and h. And if at initial time alpha is the simultaneous eigenket of a and h, it remains so at all times. Okay, after time t also, this h is eigenket of alpha is eigenket of h at time t, and this alpha at time t is the eigenket of this a also. Okay, so we have discussed the effect of time evolution operator on the on some state ket alpha that depends on the effect of time evolution operator on base ket a dash and we have finally reached that in an assumption that if at the initial time alpha is the simultaneous eigenket of A and H, it remains so at all times. Okay.